It isn't always clear to students when they are first exposed to acid-base buffers how they should approach pH calculations when an acid or a base is added. This video will provide an explanation for why we must initially treat these problems as pure stoichiometry problems, followed by using the Henderson-Hasselbalch equation. The example we'll use is a buffer solution containing 0.25 molar ammonia and 0.40 molar ammonium. The pKa of ammonium is 9.24. We can use the Henderson-Hasselbalch equation, which states that the pH is equal to the pKa of the weak acid used, plus the log of the concentration of the conjugate base over the concentration of the weak acid. If we plug in our values, we get a pH of 9.04. We can use this pH to back calculate the concentration of the hydronium and hydroxide ions in solution, which are 9.12 times 10 to the negative 10 for the hydronium ion and 1.10 times 10 to the negative 5 for the hydroxide ion. So what happens when we add 0.10 moles of hydrochloric acid to 1 liter of the solution? We know that HCl is a strong acid and it will dissociate into hydronium and chloride ions in aqueous solution. This newly formed hydronium ion is pretty strong and will readily react to any base that is also present in the solution, starting with the strongest. The strongest base that is currently in the solution is the hydroxide ion, generated by the buffer equilibrium. However, if we compare the amounts of hydronium ion and hydroxide ion in solution, we will see that there isn't enough hydroxide ion to neutralize the newly added acid. The difference in mole amounts is so great that, based on significant figures, the neutralization reaction should keep the hydronium ion the same after the reaction. Now that the hydroxide ion has been consumed, the next strongest base in solution is ammonia. The neutralization reaction will be hydronium ion plus ammonia will form an ammonium and water solution. But why can we assume that this reaction will go to completion rather than it just existing as an equilibrium reaction? Well, if we write the reaction in reverse, we get that ammonium plus water will form ammonia and hydronium ion, a reaction we should be familiar with, as the ionization of water by a weak acid is the same. We even know the Ka of this reaction, which is 5.75 times 10 to the negative 10, based on the pKa given earlier in this problem. Using this information, we can determine the equilibrium constant for the reaction of hydronium ion on ammonia, which will be the inverse of the Ka of ammonium and is equal to 1.74 times 10 to the ninth, a really large number. That number is so large that we can essentially consider this reaction to go to completion, since only a completely negligible amount of the limiting reactant will remain. So using this information, we can set up an ice table to determine which reactant is the limiting reagent and how much of each reagent remains and product is formed. We need to make sure that we include the amount of ammonium present in solution as well, since that didn't disappear by adding a strong acid to the solution. Since the hydronium ion is the limiting reagent in the reaction, we will end up with 0 moles at the end, and 0.15 moles of ammonia and 0.50 moles of ammonium. Since the Henderson-Hasselbalch equation is just a ratio of the weak acid and conjugate base amounts, we can directly plug in the mole amounts from the ice table without calculating their concentrations. This will give us a new pH of 8.72, a result that makes sense since it's lower than that starting pH that we had earlier.